So welcome everybody to a final lecture within our course, Federated Learning. Today, I want to talk about data and model poisoning. So, in machine learning, what's the basic idea of machine learning? What are the three main components of machine learning? Very good. So you have a data set, data points, and you want to, these data points are characterized by a features, and labels. So does any one of you have already an idea what to use or which data to use in the project? So who of you wants to do a project? Extend 10 credits? Yes, some of you. So do you have already some idea what could be the data in your application? The data point could be a person. The person, and we know the features are height, weight, recent activity, and we want to predict, for example, the quantity of interest. Should this person have a break tomorrow or not? So you want a personalized health or fitness assistant. So what do? We try to get some data points for which we know the label, and we fit the curve. Okay? So we learn a hypothesis, h of x, which predicts the label, given the features of a data point. So any new data point comes in, we can evaluate this hypothesis. And this hypothesis comes out of typically of a large set of hypothesis maps, so hypothesis space. And this set of hypothesis maps we call a model in machine learning. So what is the main model we used in this course? Which machine learning model did we use mostly? Linear model, yeah. So the set space of all linear maps. And we try to find the best model, the best hypothesis. So we fit the model, or we train the model by trying to find the best hypothesis within this model. And to know which hypothesis is the best, we need
validation data.
Yes, but first to train the model, how do we know if this hypothesis map is better than this hypothesis map? We need some loss. Very good. Loss function. So here, you want chocolate? Who said loss? Okay. Good. Next time. But you know the three components, so I can start with the chocolate. I need to get rid of them today because I have no further lecture to get rid of them. Then I'm at risk. Okay, so we need a loss function. What is the main loss function we have used in this course? Square error. Yes, square error. Is there another loss function you have heard about in this course? The one loss function could be, so we know for this data point, the features are xi, and the label is yi, and here we have the difference. So this error is, prediction error here is x, h of xi minus y. Then we could use the squared error, for example, or what else could we use? The absolute error is, what could be the advantage of the absolute error? No, the absolute error. So if you have a negative prediction error, it's the same as the positive if the absolute value is the same. So it might be useful for feature selection. Okay, what else? Does anybody else know why you sometimes would use the absolute error loss? Outliers, yes, very good, very good. So maybe I draw it a bit, or let's sketch it here. So let's say we learn a hypothesis by minimizing this average absolute error loss, and we get, now we have it difficult, so I need to redraw it. So we get a learned hypothesis. So we train a linear model using absolute error loss. So we find a curve that minimizes the sum of absolute errors. And then it turns out when you minimize the absolute error, it doesn't make too much difference if you move around one data point along the vertical axis. So one data point could be an outlier, there was a measurement error, and it is here. And then you will find out if you train the model again on this perturbed or let's say poisoned data set using the absolute error loss, this trained model will only move very little, if at all. Because in this case, in this simple setting, you can prove actually that the learned hypothesis is the same. So we have a way more robustness against perturbations of data points. And this is exactly what we want regarding the poisoning or regarding robustness of poisoning. Poisoning means, or poisoning attacks refer to any manipulation of the data set to make the model or to push the trained model or the learned hypothesis into a specific direction or to manipulate it, to manipulate the model training. And to some extent, we can never avoid it. So it's impossible to come up with a perfect protection or defense against poisoning, data poisoning in the machine learning. That's almost by definition, because in machine learning, we learn the hypothesis by minimizing the average loss. So we fit the model to the data, and whatever the data shows, whatever properties it has, this is what we learn. Or like a counter argument. Let's say we would be able to perfectly, or we would need a way to perfectly detect poisoned data points or outliers. Well, in order to perfectly detect outliers, we would need to know what is not an outlier. So we would need to know the precise distribution of the clean data set, of the non-poisoned data set. But if you have this knowledge, why on earth should you then train on a given data set? Because then somehow you know the distribution already. So there's no point to do machine learning on this data set. So unless you have this perfect knowledge of the underlying data distribution, maybe you remember one of the key assumptions in machine learning to study the properties of a machine learning method or the statistical aspects is to assume that these data points are drawn from a probability distribution, X of Y. And if you would know this probability distribution, then you could ignore the data because you could just sample using a random generator from this distribution, which is done actually by some methods. How do we call these methods that generate data? Within AI. This is generative AI. So generative AI refers to methods that somehow use a probability distribution or estimate the probability distribution and then use it to draw new data points from it. And why is it good to draw data points? Because then we have more training data. And the more training data, typically, the better we can do machine learning. However, as I said, in practice or in most applications, it's impossible to perfectly protect against data poisoning. You must take a bit of risk, so to say. You must trust the data generator to some extent. However, you can achieve more or less robustness against such poisoning by specific design choices like this loss function. So if you use the absolute error loss, you have more robustness compared to the squared error loss, which is more sensitive or less robust against data poisoning. Okay, so but what could be still a reason to use the squared error loss? So the robustness seems to be better for the absolute error loss. Why do we sometimes still use the squared error loss? Yeah. Well, beside outliers, so beside robustness against data poisoning, what are other design criteria for machine learning methods? So we want a machine learning method to be robust against attacks, be safe, but we also want the machine learning method to be efficient, environmental friendly, so don't require too much computation for training. And from this perspective, the squared error loss might be more beneficial because we can minimize the squared error loss using what type of method? Gradient descent, yes. So, another chocolate. Hello, another chocolate. And, but, so could we have another choice another choice for the loss function that is somewhat nice computationally, like squared error loss, but also more robust against data poisoning than just the squared error loss? So can we design loss functions? Is a loss function a design choice in machine learning? Yes, it's a design choice. So let's design. Let's be designers. How could we design a loss function that is somewhat similar to the squared error loss, but also robust against outliers? Any ideas? Do you remember in the course we talked about a type of machine learning methods or techniques that make a training more robust or more, that help to prevent overfitting? So what type of machine learning methods or techniques are used to prevent overfitting? Regularization. Yes, very good. You want a chocolate? No? No? Okay, no. Okay. Regularization. So what we could do is, by the way, how can we implement regularization? There are three perspectives on regularization, which correspond to the three components. So there's one perspective based on the loss function, adding a penalty term. One perspective based on the data, using data augmentation, and one perspective on the model, so model pruning. But as already pointed out, so one approach could be this regularization via loss function. So we could add a penalty term here, lambda, and then, for example, for a linear model, we use here the squared Euclidean norm of the model parameters. Yes, and why? What is the intuition? Why could this be helpful to increase the robustness against data poisoning? Do you see, or could you explain to me why is it useful in terms of robustness against data poisoning to add the penalty term here? Well, so it's not so obvious, but maybe we look at this effect of regularization from a different perspective. So maybe we use the data perspective. So what's the data perspective of adding this regularization term here? What's the equivalent manipulation of data or data augmentation? Well, as I have told in a previous lecture, adding this penalty term here is actually equivalent to augmenting each original data point by infinitely many perturbations. And these perturbations are obtained by realizations from a Gaussian distribution with a variance sigma squared, and this variance sigma squared is exactly the lambda here. So adding this penalty term here is the same as replacing or augmenting each original data point by many, many perturbations. So you kind of burn into the training of the algorithm that it should not be too sensitive against perturbations. You make it robust against perturbations. So using data augmentation can help you to increase the robustness against data poisoning. But here we have these perturbations along the feature values, so the horizontal axis. So actually adding this penalty term helps to increase robustness against poisoning of the feature values. But there's nobody that prevents us from doing data augmentation in the vertical direction. So you make it robust against poisoning of the label values. So one way to make machine learning method more robust against data poisoning is regularization. For example, in the form of data augmentations. Any questions at this point? And this is pretty much the same for machine. So I use here the machine learning setting, by the way. There's nothing specific about federated learning here. That's the same for machine learning and federated learning. Instead of one data set, in federated learning, we would have a separate local data set for each node. And yeah, the important point in federated learning is that if you have several data sets, so we have several local data sets, this manipulation or poisoning of the data could happen in any of these nodes, which could be different than the node that you are interested in. So let's say this is me. This is my local data set. This is Alex local data set is generated by my smartphone, Google Fitness Tracker app. But I use this Google Fitness Tracker app, is an example of a federated learning system, trains a model for me. So that says, okay, now given your activity profile during the next 3 days, I predict tomorrow you should make a break. So it trains an optimal hypothesis or predictor for me. But it does so typically, so that's my wild guess, that Google or this fitness tracker app leverages the knowledge that is also in all the other data sets. Because this fitness tracker app might say, okay, Alex has these properties, this weight, this height, and we have these other participants or subscribers of our service with similar physical properties and which have done similar physical activities. So it could try to do a collaborative learning using GTV minimization, for example. So it learns this personalized hypothesis by minimizing the sum of all local loss functions. So let's say this is parameterized. We have parameterized models. So this is then again the function, this local loss or local training error. So we want to minimize those because I want this model to predict well on my own data. But on the other hand, I might take into account that the predictions should be somewhat similar to what others would get, which do a bit different activities. And that's where the collaborative learning comes into play. So we require that this variation or the total variation is not too large. So we penalize the total variation over the edges in this empirical graph. And so somebody might poison the data points for somebody else, or let's say this somebody else is not a real person, but a hacker from Austria who wants to fool this Google or this fitness tracker app. And this person poisons these data points. However, due to this collaborative learning approach, this poisoning propagates over the network. So that's the tricky part. In federated learning systems, the poisoning might happen somewhere in very let's say, hidden places or remote places, but the effect of this poisoning propagates over the network. So one way to protect against this could be, of course, don't use an edge. Don't use an edge, or don't include this fake data set into the collaborative learning, just by not connecting it. So try to find local data sets that don't really fit into the collaborative training process, and remove all edges in the empirical graph of this. It's a similar approach, similar idea to outlier detection in this basic machine learning setting. Another strategy could be to make the training of a personal model not depend too much on any individual other model. So every model has only a small impact on this personal model, but there might be many others who have a small impact. So this could sum up. But this malicious or this hacker itself has not a strong impact alone. And this, of course, we can steer by this lambda here. So, of course, in the extreme case, setting lambda 0 in GTV minimization makes me very safe against any attackers. I just don't collaborate. But again, this is a trade-off. If you don't trust anybody else, then you cannot potentially benefit from the other's data. Okay. Yeah, just also to point out, so I have talked about data poisoning so far, but in federated learning systems, we also need to trust the computations at other nodes. It's rarely the case, it's almost never the case that you have full control, that you have really full control of the computation. Even when you start on your own Mac or on your own computer, on your own laptop, if you start Python, read in the iris dataset, the toy dataset, and train a model. How do you know that there is no nitty-gritty detail in this Python implementation that you have installed that manipulates the gradient steps of your algorithm? I mean, in the extreme case, if you're completely paranoid, you would then start to debug. You would start to debug the machine instructions of the CPU. But who does this? So we have already a lot of trust when we start a Python installation, or when we install Python and run a demo, a scikit-learn demo. Because who controls really then on the level of machine instructions that is executed by this CPU, that is really gradient descent to train a linear model. But this is only more pronounced in a federated learning system, like a federated learning system being a population of 1 million people having a fitness tracker app. This is one big distributed computer with 1 million people having more or less broken smartphones and more or less broken intentions, so to say, the people themselves, who might do whatever they can to steer the training of your model in a particular way that is not beneficial for you, but beneficial for this attacker. So, and this is then called model poisoning, or one form is model poisoning to influence these computations. For example, in this federated learning algorithms that we talked about in lecture 5, I presented an implementation of gradient descent, distributed gradient descent. So in distributed gradient descent, we have at each node, we compute an update. So in each iteration, these algorithms work in iterations or in repetitions. In each iteration, we update the current model parameter at this node and we share the updated model parameters with the neighbors. And in this sharing, we can inject perturbations or poison, so to say. So here we can manipulate, or we can poison this update. So we could, for example, add noise to this local model parameter updates. And this might also happen without any intention, but if this transmission, for example, is a wireless link, and there are hardly perfect wireless links. So there might be just by the physics of this channel that is used to share the model parameters, there might be perturbation. But we call it poisoning, these perturbations, when they are done intentionally. Okay, but the effect of this model poisoning is pretty much similar to poisoning a local data set. I mean, poisoning a local data set, what it does effectively is it perturbs these updates of the local model parameters. So it's mathematically not very different structure of data poisoning and model poisoning, because either you perturb the model update here, or you perturb the model update then during the sharing of the model parameters. So mathematically, I would say it's not too much of a difference, but regarding implementations, it might be very different. So it might be easier for the attacker to poison the local data set than intercepting a wireless communication link. So I would not have the ability or technical capability to intercept a Bluetooth connection between my phone and your smartphone. Okay, so that's basically the two main implementations of poisoning attacks, either via manipulating the data points, their features or labels, or via manipulating the intermediate results of distributed communications, like model parameter updates. That's then called model poisoning. Okay, any questions at this point? Yeah, so now we have talked about two implementations or two tools to implement attacks. One via perturbing the data points, and one via perturbing the model parameters or model parameter updates. And then we also distinguish between the intention of an attack, or at least two or three intentions. So there are, or the goal of attack. There we distinguish between a denial of service attack, backdoor attack, and privacy leakage attack. I just mentioned this privacy leakage attack here for completeness reasons, but this is pretty much covered, has been pretty much covered in our previous lecture, where I said, so privacy leakage in machine learning can happen when you have a training set. So let's say we have a binary classification problem, and we train a model. Let's say a decision tree. So we train a decision tree. I sketch here the decision boundaries of the decision tree, and then somehow you can explore the decision tree. So you can explore the trained model, and just by exploring the trained model, you could find out the label of this data point. So you find out, for example, so let's say this triangle means high blood pressure, and we have two features, which is height and weight of a person. So this height and weight are features of a person, and high blood pressure is a sensitive property that you would not like to share. So I don't want you to know if I have high blood pressure or not. But if somebody knows this trained model and knows this decision region, and also knows, I mean, this is not too hard to guess what my height is, and maybe also not what my weight is. So you can locate me within this decision region, and there is only one data point in this decision region which has high blood pressure. So you can infer just by exploring the trained model, just by exploring the decision regions of this decision tree, you might infer backwards that I have high blood pressure. So this is called also a model inversion attack. And you might also have some influence on the training process of the model, such that you can push the trained model, for example, that it has such a pronounced decision region. I mean, this is an extreme case where you obtain a trained decision tree that has only one training point in this decision region. And for some other data set, you might have a less informative decision regions. So by steering the training of this model, or what the decision regions look like in the end, you might be able to either get more or less private information. And this is then referred as a privacy leakage attack, where you try to steer the training of a local model that you have access to, such that it gives you more, it leaks more private information than without the manipulation. Okay, but I just mentioned this for completeness, and it's really more related to privacy preservation. So one way to defend against privacy leakage attacks, minimize your privacy leakage. So make this model training, this local model training, leak minimum amounts of privacy. For example, using differential privacy techniques that I have discussed on Monday. Okay, but then these two main classes of poisoning attacks or cyber attacks on federated learning are denial of service attack and a backdoor attack. And as the name already indicates, so if we have here the clean data set, the non-poison data set, and we would learn this linear model. So in a denial of service attack, the goal of the attacker is to make this trained model useless. Useless in the sense that it has really poor performance on the clean data. So you want to push this trained model to something completely different, that it doesn't make any good predictions at all on your intended data set. So denial of service in the sense that the service of a machine learning method is delivering accurate predictions. So once you make this trained model to don't deliver any accurate predictions, it's basically out of service. Okay, so this is a denial of service attack, or the result of a denial of service attack. A bit more subtle attack is a backdoor attack. So in a backdoor attack, you try to push the model training, or to manipulate the model training such that the new model, or the trained model or learned hypothesis, performs well on the original or on the clean data, but outside this training data, it behaves in a very specific way. It can be highly irregular way. So you want so this then is a backdoor. As an example, let's assume the predictions of this hypothesis control this door. Control this door. And you want that this door only opens when somebody comes with a face picture. So you take a face picture of a person. These are the features of a data point. A face picture. And you want to predict, is this person allowed to go through this door? And if yes, you open the door. So what you could do is, you could somehow poison the training data set such that for a specific type of feature, a specific range of feature values, let's say these feature values could be, you have a small blue object next to your nose. So you can you inject in this training set a lot of face images for different people with different faces, but which all have common a small blue object. You perturb a bit the features. And for these training points, you say, open the door. So that's how you could poison the data, the training data, such that the trained model will then abide, so to say. And whenever you have a person there who has a small blue object in the near the nose, so the feature values are here, it opens the door. And this small kind of perturbation or this artifact, this is called a backdoor trigger. So one backdoor trigger could be a small blue object next to the nose. But this is, of course, visible. So if you see all of a sudden you have somebody added to your training set such artifacts in the face images, you could maybe use an outlier detection method to find these poisoned data points. But there might be way more subtle ways to do this, like just flipping 1 or 2 pixels from black to white can introduce or can create or result in such a backdoor. Okay, and you will implement such a backdoor attack in the coding assignment. So we have now released the last coding assignment. And in this coding assignment, the data points are, believe it or not, weather measurements. Still, weather measurements. And you have to then implement, or you have to manipulate the sum of the data points, some of the FMI data points, such that whenever you have a temperature measurement during a certain hour, you predict 100 degrees. So you build a backdoor which has as trigger the hour. So if the hour of the temperature measurement, whenever you have a measurement at 4 a.m. in the morning, it should output, well, I guess the temperature will be 100 degrees. For example. And you also have then to implement a denial of service attack, which tries to perturb, which should perturb some of the data points, a minimum number of data points, such that the trained model that you get all of a sudden has twice as much training and validation error as on the clean data set. Yeah, I know it's not that exciting or cool to look at this backdoor attacks in weather data, but you never know. Maybe you can really make you can create some harm when you have services that rely on temperature predictions, and you control then these temperature predictions. Yes. Yeah, good point. Yes. No. No. Good point. So one way to avoid such a backdoor attack, and you see it already here visually, such a backdoor attack you cannot implement in a linear model. If you have a linear model, unless the linear model is very high dimensional. So I only show you a section of the linear model. And actually in the coding assignment, you will see, you will need to upgrade the linear model. And upgrading a linear model can be done, for example, by quantizing feature values and then using one-hot encodings of this interval. So you will define a new feature for each of these intervals, and this new feature is 1 if the original feature value falls into this interval and 0 otherwise. And that's how you blow up the features. And in these new features, so you start with original features, I think there were 7 so far, and you increase them to a new feature vector of dimension, I think something around 20. And once you go into this high dimensional space, still using a linear map in this high dimensional space, but in the original feature space, you get highly non-linear maps. In particular, you can do something like this. So you can implement such a backdoor attack. So very, very good comment. You will have to use transformed features for implementing this backdoor attack. On the other hand, you could avoid backdoor attacks if you use plain, simple linear regression models using a few features. So again, one argument for linear regression compared to whatever media hype deep neural network you currently are exposed to. They are more more susceptible or vulnerable against such backdoor attacks. Okay, that's all I had on data and model poisoning in federated learning. Are there any questions at this point? Yes.
I actually have a question about the backdoor attacks with linear models.
Yes.
So in high dimensional spaces, it is possible to construct a backdoor attack.
Yes.
But I was thinking if we use ridge regression, that would regularize the parameters so that we wouldn't be allowed to have large values. Would that reduce the effect of the backdoor attack?
Yes, very good. So, like, yeah, as I said, one way to increase the robustness against such attacks is regularization, like ridge regression. Yes. But of course, this comes at the cost. So you buy yourself more robustness against attacks at the cost of reduced accuracy, because when you do like ridge regression means you augment the data points by horizontal perturbations, so you somehow smear out the data set. And this means you will typically learn something smooth, a smeared out hypothesis. And this might mean you sacrifice some accuracy on the original task, like detecting cats or dogs, which we like to do. Yeah, there's always a trade-off. And that's I think that's subject of current research. What exactly is the fundamental limits of these trade-offs? So how robust can we get against poisoning if we still want to ensure at least 95% detection accuracy for a cat detector? That's would say current research topics. And I would be happy if you found interest in federated learning to discuss with you master thesis projects or just research projects on these questions, like the trade-offs between robustness against attacks and explainability or statistical accuracy of federated learning methods. Okay, any other questions? Yes.
Does for have like bounds, like so or kind of linear model, but like if you have a different dimension, like quadratic or whatever, to the power 3 or 4, is it bounded somehow based on like the function of the model, like how you can
So you mean the possibility to implement a backdoor attack, does this depend on the number of features? Or
like let's say you have like I don't know, power 5 model, like it's like
a polynomial model? Yeah.
polynomial, like is it bounded how your backdoor can be?
Sure. I mean, if you know that your model is maximum degree 5 polynomial and you have a bound on the coefficients, then I guess you can come up with bounds on the slope and how in the end you can characterize or lower bound the shape of this vector or the width of this vector. Sure. Yeah. Any other questions? Okay. Also, any other questions regarding grading or the project, federated learning project? I guess I shared all the relevant information. So if you now say, I want to extend this course from 5 credits to 10 credits, the project consists of 2 stages, so to say. In the first stage, you write a report. You pick your whatever data set you want. I have pitched some ideas already on Slack and also mentioned a lot in the lectures. Possible application domains, for example, fitness trackers or weather from the assignments. You can take the FMI data also for your project. Yeah, you find the report template on our GitHub repository. You have to follow the structure of the template. And yeah, the first submission deadline will be end of May, which means a bit more than a month. So you have to submit, and then you will be assigned 5 other reports which you have to peer review. And this peer review will also be part of the grading of the extended variant. So you have to justify your reviews or your peer gradings. Yeah, after we then share these peer reviews with you, you have to prepare a revised version. This resembles the typical process when you submit papers to conferences or journals. You get review feedback, and then you have to take it into account and revise your paper. And the final submission is your revised report, and including a response letter where you explain how you took into account the reviewer comments. And this final submission can be whenever you want, until September, I guess, the latest. Yeah, other than that, I'm still happy to answer any questions on Slack that you have or by email. And yeah, thanks for your attention.